So good morning students. So please type in the chat box. Am I audible to all of you? So am I audible and is the screen clearly visible to all of you? Is the audio clear? Yeah, it's clear, right? Good morning. I hope the audio is fine, correct? Yeah, good morning all of you. So please confirm the audio once and video. Good morning everyone. It's fine, right? Yeah, okay. Yeah, all clear. So let us start this lecture basically. So this is lecture number 3 in this fast track of fluid mechanics. Okay, and in this lecture we'll be majorly looking on hydrostatics. Okay, so basically we will talk about hydrostatic forces, pressure and its measurement, and also buoyancy and flotation actually. So basically the hydrostatics part, whatever we have, that we will see in this case. Okay, and obviously you can see this is the sequence. First we'll look at pressure and its measurement, then we'll focus on hydrostatic forces and also on buoyancy and flotation, and then we will go through certain numericals which could emphasize this understanding. Okay, and if you see basically in the last lectures we were talking about properties of fluids in a much detailed sense. Actually we were talking about this bulk modulus, which is minus dp by dv by v, and also E is equal to dp by d rho by rho obviously. Okay, and also we have seen the difference between incompressible fluid and also incompressible flow, correct? We have seen the difference between incompressible fluid and incompressible flow actually here. Incompressible flow obviously. Okay, so to decide whether this is incompressible fluid or not, we need this bulk modulus value, and high E implies difficult to compress. Difficult to compress. And incompressible flow. So this is basically depending on Mach number. We have seen this Mach number. Normally, if this Mach number is less than root of 0.1, which is I think generally 0.368 with 0.3618, right? 0.1 square root. Okay, yeah, 0.316 roughly. Okay, so this Mach number is less than 0.316 or 32. Sometimes we write for calculations comfort 0.33. 1 by 3 also is taken generally for very less accuracy flows and all. So if this is the case, the flow is incompressible. The flow is incompressible in general. Okay, so to identify whether a flow is incompressible, we look at the Mach number, and to identify whether a fluid is incompressible or not, we look at the bulk modulus value of that. Okay, so then after we have seen certain non-Newtonian fluids. So basically we have seen the Astral-Wallis model, tau naught plus a into du by dy whole power n actually. Okay, so this is the yield shear stress, this is the flow consistency index, and this is the flow behavior index, and we have seen how different graphs are coming, basically dilatant, pseudoplastic, all these things. Guys, in yesterday's class basically one thing we have to correct actually. I think when we are writing the things in time dependent case, if this is t and if this is eddy viscosity for example, then you can see this is time thickening and this is time thinning obviously. Okay, so this is time thickening obviously because the slope increases with the time. So time thickening or basically tau versus you can generally write this eta with t, and with respect to time this eta is increasing, so this is called time thickening and this is called time thinning obviously. Okay, time thinning. In yesterday's class, I think after watching the video later we have identified that this I have told as thixotropic. Actually this is a u effect tick and this is thixotropic. Okay, so please make a correction here. So this is thixotropic. Okay, because I think yesterday in the overlook when I'm writing the names, these got interchanged. Yes, so please correct them. Okay, yeah, kal ke lecture mein these two got inverted. Basically this names euphectic and thixotropic we have interchanged actually, but that's not the way. This is the way actually. Okay, because obviously time thickenings are called euphectic fluids, and that's what we generally study the more, which is called the rheology. Okay, clear? So fine, these are the things. Now coming to today's topics, that pressure and its measurement. So in yesterday's class we have talked about a brief of pressure, basically the intensity of external compressive normal force is called pressure. Like for example, we have seen that if you have a body in general at any point, for example on this small elemental area delta A, let us suppose if the force acting, the normal force to this is delta F. Okay, so it's along the normal, but of course in the compressive direction. So pressure we generally define as intensity of that. Okay, so for a small area, what is the force acting with respect to this area is what we have. Okay, so this is the definition for pressure. Some examples of time dependent fluid, I told you na, nail polish, all these things. Okay, in general. Or sometimes cement, basically when you mix cement with water, okay, let us suppose if we have the ceramic mix, then definitely the ceramic mix, what happens in the beginning time, it is like very fluidic in nature, but as time passes on it gets hardened and hardened. Okay, all these are practical examples of things sort of on the effective fluids. Okay, now let us see if this is pressure. Then we have seen units are pascals obviously, or Newton per meter square in SI. Okay, and the dimensions of pressure is like Newton is force. Newton is actually force into force is equal to mass into acceleration. So ml t power minus 2 mass kg into meters per second square by meter square. So L power minus 1 actually here. Okay, so these are the dimensions of pressure, correct? Because Newton can be written as kg meter per second square. So kg meter per second square divided by meter square. So meter by meter square gives you meter power minus 1. So this is L power minus 1 t power minus 2 obviously here in this case. Okay, and now coming to the case of this certain important fundamentals, we generally take something called the Pascal's law obviously. Okay, so what does a Pascal's law state generally in general? Okay, so in a static fluid, pressure at a point is same in all the directions, actually. Okay, so this is same in all the directions. Like for example, it's a very common proof to show. Normally you take a wedge and then if you apply force balance in all the 3 directions, then you obviously can show that. You can see generally, let us suppose if you have a static fluid for example, then at this point, if you take a point for example here, at this point the state of stress in all the directions, in every direction, is actually minus P. Of course, minus sign denotes it is compressive in nature, so the pressure is actually same in each and every direction obviously. Okay, so this is what we have here. And if you see the state of stress in general, for example, look how this can happen. You can easily show with the help of a simple wedge construction. See, okay, so let us suppose if you do this, then this is the wedge obviously. Why I'm taking only wedge? Many of you may have a doubt why I'm taking only a wedge, because I want to take a plane which is inclined at an angle theta with this horizontal and finally show that the end result is independent of this theta. Okay, so that's what my main intention. So for that I'm doing. Now let us suppose in a big element of static fluid, let us suppose if there is a big expanse of static fluid, for example, if I take a small element like this. Okay, so I have taken some small triangular element and I am doing the analysis for this. Okay, now let us suppose if this is a small element, if I call this as dx for example, and this is dy clearly, okay, and this is dl obviously. Okay, so let us suppose this is dl in this case, clear? So this is dl. Now if this is dl, let us see the pressures acting on different faces. So on this face you have certain pressure, and also on this face you have certain pressure. Okay, and on this face also it's inclined at some angle. Okay, so it's inclined at some angle like this, and obviously on the front and back faces the pressures are cancelling each other by default. Okay, so let us suppose you have a front face and also you have a back face. Like for example, if I name this coordinates A, O, B, C, D, then the effect of pressure on the face AOB and on the face CDE will be cancelled each other because they are just opposite to each other. Okay, now if you try to maintain the equilibrium, because this fluid is in static condition, if this fluid is in static condition, every block of that fluid should be in static equilibrium. Okay, so therefore if you apply sigma f bar is equal to 0, basically you have two equations. We are dealing in slightly 2D because in the z direction we are not taking any changes. Obviously they get cancelled each other. Now if you apply this x direction case, for example, let us suppose the pressure acting in this direction is py and the pressure of px, for example, and the pressure acting in this direction is py, and this pressure acting at normal is Pn actually. Now whenever this is a very, so please explain Knudsen number. Yeah, I'll explain you. Okay, fine. I'll explain you after this. Okay, so see here, if this is Pn, then let us see what happens here. This Pn and this Py and Px are the forces acting on the mutually perpendicular, or these two are perpendicular faces, and this is a slant face actually. Okay, now if you apply this forces equilibrium actually, and let us suppose this block is actually very small. Okay, so you have actually taken Pascal's law is only valid for static fluid. Yes. Okay, so this is delta actually. Okay, so if that's delta, then if this is py, if you take this block size is very small, for example. Okay, so because we are just picking some small elemental from that, so this is dx dy and this is dl. Obviously if by Pythagoras theorem you can calculate dl is equal to root of dx square plus dy square. Okay, now if you add sigma fx, sigma fx implies, look, if you generally assume that all three forces are meeting at the centroid, for example, okay, because it's a concurrent force system, for a small size of the block, obviously these three will actually pass through one particular point. Okay, so therefore if you do this analysis, for example, see, you have a force which is acting along this direction, and what is this force? Obviously, so this is px, and px into this is pressure, so pressure multiplied by area should be there, obviously. So if you multiply with area, then you can understand this length is actually dz, let us call, for example, this length is a dz. Okay, so if you call this length dz, then the area on which px is acting is nothing but dz multiplied with dy, correct? So this is dz multiplied with dy actually. Similarly, there is a force which is acting in this particular direction, which is py into this area is dx into dz, obviously. Okay, and also the pressure which is acting normal to this plane. Okay, so you can see there is some pressure which is acting normal to this plane, so this is p, for example. Okay, so this is p acting at some random direction, say pn, into, now what is this area actually? dz into dl, for example. Okay, so dz into dl is what you can write in general. Okay, so dz into dl. And what about the angles here? See carefully. With horizontal, this plane is making an angle theta, so normal to the plane will make an angle of 90 minus theta with horizontal, correct? So this is 90 minus theta, obviously. Yes or no? This is 90 minus theta because with horizontal this plane is making an angle theta, so obviously normal to the plane will make an angle 90 minus theta. Yes, like you know from simple geometry, if two lines are intersecting, then definitely at this particular point, if this is theta, if you draw something normal to this, then definitely the normal with the horizontal will be 90 minus theta, correct? So simple logic. Now if you apply Lamy's theorem, for example, Lamy's theorem, because you know these three are actually in equilibrium, so if you apply Lamy's theorem directly, so let us see px into, or let us resolve better. Okay, so because anyway you can see this total angle is sine 90 plus 90 minus theta, so sine 180 minus theta and all. Similarly this angle is 90 and this angle is theta, obviously, so 90 plus theta. So we have a lot of things actually, so let us write in x direction. So sigma fx, if you see this, px dz dy, and obviously the resolution of this will be minus, so minus pn dz dl. This cos 90 minus theta component will be acting along x-axis, so cos 90 minus theta is sin theta, which is equal to 0. But clearly you can understand one thing, this dz and dz gets cancelled up, and this is dl sin theta. From this particular triangle, if you take sin theta is nothing but dy by dl, and cos theta is nothing but dx by dl, obviously. So this dl into sin theta, which is this term, can be written as a dy. So if this is written as dy, then definitely this dy and this dy gets cancelled each other, so we have px is equal to pn, and clearly this outcome is independent of theta. That means the pressure acting in this direction and the pressure acting at some arbitrary direction is also same. Clear? And now if you write sigma fy, is equal to 0, of course. Now you can see this is acting along positive, so py dx dz minus pn pn obviously dz dl into the vertical direction in the downward, that's why I have taken minus, so this will be cos theta again is equal to 0, and dl cos theta is nothing but dx. So if you write this as dx for example, then clearly this dx dz and dx dz gets cancelled, so you can also see py is equal to pn obviously. Okay, so which means one thing is very clear in all these points, since this outcome is independent, just two equations, okay, static equilibrium. So if you have this theta for example, then since these two equations tell you that this pressure acting in the x direction and pressure acting in this direction and pressure acting in some random direction, okay, that's why intentionally I have taken which, because this answer is independent of theta obviously. Okay, so if this answer is independent of theta, then definitely all three are equal. You may have one doubt, obviously this weight will also act, yes or no, this weight is also there, but why I did not consider that weight is actually weight is a higher order term. Like for example, if I want to calculate weight is equal to density into volume, half into dx into dy, this multiplied with dz into g. Now clearly you can see in these two in every term you have only two differential terms, but here you have three differential terms, which means this term will be very small as compared to these two terms. So that's why clearly I have neglected the weight, okay, because I'm taking a very small element. So basically at the outcome, Pascal's law tells you that if you have a static fluid at a particular point in the flow, at a particular point in the static fluid, the pressure exerted will be same in all the directions but at a point. Okay, clear to all of you? Fine. So please type in the chat box, is this clear to all of you till this point? Okay, now let us see one very important law, which is actually the hydrostatic law. Hydrostatic law, which is normally written by the equation rho x bar minus del p is equal to 0 obviously. Okay, so that's actually the hydrostatic law. Why I'm writing that in vector form and how that form is coming, I'll explain you very soon, but writing in that form is very helpful to you actually. Okay, the advantage with vectors is you can actually solve the components in all the directions with single calculation. Okay, let us suppose if I write f is equal to ma for example, rather than splitting this, if you know how to solve this equation in vectors, let us suppose by applying vector differentiation or vector integration and all, this equation becomes very simple. You can deal the components of all three directions within a single calculation actually. Okay, so that's advantage of vectors actually. Now anyway, let us see how that equation is coming. First of all, we have to identify one thing which is called pressure gradient. Okay, so pressure gradient del p obviously. Okay, so del p gradient, you know from your mathematical knowledge, this is grad p obviously. Okay, now what is this grad p? Obviously p is a scalar. Okay, so pressure is definitely a scalar. P is a scalar. Okay, it definitely acts in the direction in which the force is acting. So p is a scalar obviously at any particular point. Now if you see, let us suppose you have some plane, for example you have some plane like this. Now depending on the type of flow, when fluid is flowing and all, it can have different pressures at different locations. Okay, so you can actually classify pressure as function of x, y and z in general. Let us suppose if this is a twisted plane in 3D, so at any given point you can have some pressure. So if you have pressure, and definitely this pressure is changing from point to point, so you can define that p is actually function of x, y and z in general. Okay, now you know gradient of the definition of gradient normally. So del p is equal to dou p by dou xi plus dou p by dou yj plus dou p by dou zk actually. Okay, this is in Cartesian, we are writing in Cartesian as of now. We can write it in polar coordinates also, which we'll see normally in fluid kinematics and also followed by flow through pipes. Okay, we'll see whenever you have to draw flow through pipe, variation of pressure with respect to radius, variation of pressure with respect to theta, we'll see all these things. Okay, so right now as of now, to make the easiness, I'm doing only in Cartesian coordinates. Now try to understand one thing, what do we mean by dou p by dou x actually? Okay, so this is pressure gradient in x direction, pressure gradient in x direction, Similarly, this is in y. Similarly, this is in z directions. YZ directions. Okay. Now, try to understand one thing here. If this is in Cartesian, look. Let us suppose if we have a flow, for example. Okay. Let us suppose if some fluid is flowing. Okay. We'll see later. We'll keep this fluid in static condition. But right now, let us suppose it is flowing. Let us suppose if this is x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, for example. And let us suppose if the pressure values are 20, 15, 10, 5 pascals, let us suppose, for example, this is in pascals. Then can anyone tell me, if I plot the next point, for example, if I plot somewhere here x is equal to 4, can anyone tell me what is the pressure that's going to be here at this point? Come on, if this is how the pressure pattern is changing, then at this particular location, can anyone tell me what is the pressure that is supposed to act as per this data? 0, obviously, right? So here the pressure has to be 0. How do you know that the pressure is 0? Because somehow you understood that when x is changing by 1 unit, pressure is decreasing by 5 units, correct? This is what you have observed from this particular calculation. Yes or no? You observed that when x is increasing by 1 unit, then pressure is actually decreasing by 5 pascals actually. Okay. So now this variation of pressure with respect to x is called dou p by dou x. You may ask me why you cannot write dp by dx, because this pressure is not only a function of x, it can be functions of y and z also here. Okay. So whenever this p is depending on x, y, z, I cannot write exact derivative, I can write only partial derivatives. Okay. So with respect to 1 unit change in x, what is the change in pressure p? That's called pressure gradient. Gradient means change with respect to location. So this is the pressure gradient in x direction. Okay. So similarly, if you take the y direction, this dou p by dou y gives you pressure gradient in y direction, and similarly in z direction. And for the convenience, we are taking the coordinate system as right hand coordinate system, x, y and z actually. Okay. So xy is in the horizontal plane, z is the vertical coordinate. Now let us see, if you apply this simple balance again, if you take some cubical element, let us suppose if I take some small cubical element. Okay. Because why I am doing this, doing this one time will make you understand many things later when doing fluid kinematics and all. So let us suppose this is a center. It's a very small cuboid actually. So this is the centroid of the cuboid. So let us suppose at that point the pressure is P, obviously. Okay. Now you can define the coordinate system x, y means basically this y, and clearly this is z, for example. Okay. And let us suppose if this distance is dy, this distance is dx, and this distance is dz, obviously. Okay. So this is dz. Now if this is dy, let us suppose if I call these faces as right, left, top, bottom, front face and also back face, for example. Okay. Now let us suppose if I call these faces as this, then on the right face, if pressure at this location is P, and if pressure is changing with respect to all the directions x, y and z, using Taylor series first approximation, pressure at y plus dy by 2. Okay. So pressure at y plus dy by 2 actually. Okay. Because if this total length is dy, the distance between this centroid and the right face is dy by 2. Similarly, the distance between this point and also the left face, perpendicular distance, is dy by 2. Okay. So using Taylor series, you can see P of y plus dy by 2. So let us suppose if this is xyz, for example, the centroid of the cube, then this point at any point on this plane, the coordinate is y plus dy by 2. Yes or no? So this will be the coordinate at any point on this right face. Okay. Now if P of y plus dy by 2 is there, if you apply Taylor series, what you will get? P at y plus h by 1 factorial into dou p by dou y. Correct? This is what you get. The next terms I am neglecting because we have dy whole square, dy by 2 whole square by 2 factorial plus dy by 2 whole cube by 3 factorial and all. So if I neglect the higher order terms, then this is how I can write the first order Taylor series. Yes or no? So if I write this first order Taylor series, then this pressure is P, obviously, because at this location, actually I should write this as P of xyz plus this x plus dx comma y plus dy plus z plus dz by 2, all these things. But anyway, you know, the change is only in the y direction I'm talking. So this can be written as p plus dou p by dou y into dy by 2 is actually what you have here. Okay, so the pressure which is acting on this face from the right is p plus dou p by dou y into dy by 2. Similarly, if I write on the left hand side, I'll get p plus dou p by dou y into minus dy by 2, which is p minus dou p by dou y into dy by 2. So basically I'm just elaborating this. If you see a cube like this, for example, so this is y, x and z actually here. Okay, so x, y and z, and let us suppose if this is the centroid where the pressure is p, then clearly you can understand one thing. The pressure acting on this face will be p plus dou p by dou y into dy by 2, provided this length is dy. And if this is dx, and similarly this height is dz, for example, then the pressure acting on the right face at this point is p plus dou p by dou y by 2. Similarly, pressure acting here is p minus dou p by dou y into dy by 2. Okay, similarly on the bottom face, this bottom face is actually at this z coordinate. So let us suppose if you have p minus dou p by dou z into dz by 2, and pressure acting on the top face will be p plus dou p by dou z into dz by 2, obviously. Okay, similarly on the front face you can have the pressure as p plus dou p by dou x into dx by 2, and on the back face obviously the pressure acting will be p minus dou p by dou x into dx by 2. Actually, writing all these pressure components, is this clear to all of you? So why sir dy by 2, why not dy? Because the distance between this point and this point is only half of this total dy. That's it. Clear? Can you understand this? Is this components writing on 6 faces clear to all of you? Because that's important really. Okay, if you can understand this, life becomes very easy when we go to fluid kinematics, Navier-Stokes equations and all later. Okay, but you should understand, you should know why these terms are coming. Okay, for one phase I have given you some example using this Taylor series expansion showing up to single variable, I mean up to first order. So similarly if you do for all phases, this is how you will get. Okay, now along with these forces, one more thing that you have here is the weight W. Okay, so the weight of the fluid block is what you have. Now obviously let us suppose if you pick this block from a static fluid. Okay, so let us suppose if this is a static fluid, for example, if this is a static fluid, then try to understand, if you take a block small q from this, then this is the exaggeration of this. Okay, now obviously sigma f has to be 0 on this block because it is in static condition. So in x direction, if you apply in x direction, look, I just want to do one thing. Instead of taking weight, I want to generalize something called body force. Okay, so let us suppose there is something called the body force vector, for example. Okay, so let us suppose through the centroid some body force x is there. This is x. Okay, so body force vector, for example. Okay, x bar is nothing but body force per unit volume. Okay, so let us suppose if I take this body force per unit volume, and obviously this x can be written as xxi plus xyj plus xzk, for example. Okay, so let us suppose there is some body force. Normally if you see, forces are three, basically if you broadly classify, there are 3 types of forces. One is the line force, which acts along a line or a path. Like for example, if I take a ball, for example, and if I tie a thread tightly to it, okay, if I wrap a thread tightly to it, then the reaction or the traction between the ball and the thread will be along a line, yes or no? So the thread will exert a force along a line. Now let us suppose if I take that body and keep it inside the fluid, okay, then pressure force will be acting at every point on the surface. Yes or no? So pressure force will be acting at every point on the surface. So those are called surface forces, where force is distributed at every point on the surface. Similarly, if I, for example, weigh that, then gravity will be acting at each and every point in that ball. So the gravitational force acts at each and every point within the body and also on the body. So the force which is acting due to gravity is distributed throughout the body. They are called body forces. Okay, so we have line forces, surface forces, and also body forces. So let us suppose there is also some force which is acting at every point on this body. Why I am taking body forces? Of course, later you will see I will reduce this to gravity, but in general, sometimes what can happen is fluids can be under the effect of magnetic fields, under the effect of electric fields, not only gravitational field, they can be under the effect of magnetic and electric fields also sometimes. Okay, so whenever the fluid is in magnetic field, for example, let us suppose if this is some molten iron, for example, okay, let us suppose I have taken some, big basket of, or big buckle, ladle of some molten iron, then let us suppose if I keep some magnet close to that, this static fluid of molten iron is exposed to some magnetic field, yes or no? Then the magnet will exert this magnetic force at each and every point in the molten iron, correct? Such how some fluids can act. Similarly, in case of piezoelectric, the fluids can be experienced to certain electric fields. So clearly, sometimes this fluid can in general have a body force which is acting to each and every point. Clear to all of you? That's why I am generalizing. This is the body force per unit volume of the fluid actually. But the body is experiencing surface force. Surface force is only due to pressure, okay? But beyond pressures, we can also have some gravity or some magnetic fields, some electric fields, all can be there. The surface forces are only due to pressure force, okay? Pressures, obviously. Okay, Ranjit? Is this clear to all of you? Clear? Ranjit, I hope I have answered your question. Okay? Yeah, clear. Great. Now, if you apply, obviously under this effect, this body is in static equilibrium. So, can I say sigma fx is equal to 0? If I do sigma fx is equal to 0, what you get is generally, and so what you get generally is, like if for example in the x, okay, in the y direction, let me resolve because you feel it little easy to do in the y direction. Sigma fy is equal to 0. Analysis will be same in any direction. For example, so sigma fy is equal to 0. If you take fy is equal to 0, this is acting towards positive y. So p minus dou p by dou y into dy by 2 multiplied with the area of the face on which this pressure is acting is nothing but this dx multiplied with dz, minus pressure acting on this direction will exert a force in the negative direction. So p plus dou p by dou y into dy by 2 dx dz, plus let us suppose if this body force is actually having a component along y direction also, for example, in general, okay. So please एक बार components बता दीजिए. Yes, I'll explain you how these things are coming, but just let us finish this equation, okay. Now in the y direction, because of this body force, this component will also be there, correct? But this component is only for unit volume. So that means in order to get the complete effect of this x, what I should do? Volume multiplied with density gives you mass. So this actually gives you the force acting per unit mass actually, okay. So rho xy is equal to 0 obviously in this case, correct? Into, sorry, this is per unit volume, so this is per unit volume, so you should multiply volume now, obviously. Xy into dx dy dz, this is the volume of the cube, is equal to 0 obviously, okay. So this is what we have, because this xy is per unit volume, so multiplying this xy with total volume gives the this action of x over the complete volume multiplied with the density gives the action of this x over complete mass. That's it, because this is per unit volume. So if you multiply this with volume, you'll get the total effect of the xy on the volume, and multiplying it with density gives you mass, okay. So is this clear to all of you? Is this clear to each and every one of you? Sir, Ax is Newton because we assume the fluid is in static condition, no? That's why, okay. This fluid is expected to be in static condition, so therefore there is no acceleration to it, okay. dv by dt is 0, okay, because net force has to be 0 obviously. Now if you simplify this, one thing that you can observe is this p and this p gets cancelled. Similarly, you can see minus dou p by dou y dy by 2 dx dz minus dou p by dou y dx by 2 dx dz. So this gives you minus dou p by dou y dx dy dz plus or generally this density, if you take for example per unit volume, because we are taking only volumes, so density let us not take right now, dx dz dy actually is equal to 0, and these three terms gets cancelled. You have dou p by dou y is equal to, or dou p by minus dou p by dou y plus xy is equal to 0 actually here. Okay, so this is what you have clearly. Okay, so वो xy वाला explain कर दीजिए. Which xy? This one. Acha, this xy term. Okay, so you can see, let us suppose for example, let me tell you one thing. Let us suppose if x bar is gravitational force per unit volume. Gravitational force per unit volume. Let us suppose you have only gravitational force per unit volume actually in this case. Now if this is per unit volume, then clearly you know, let us suppose we have a body of mass m or density O and volume V for example, then total gravitational force acting on this body is OV, mass times gravity. Now if you divide this with volume, this is x actually. Okay, so x bar is equal to rho g, but actually if you take this z in the upward direction, weight will be acting in the downward direction, so there is a minus, and obviously k bar. This is the x bar in this particular case. Okay, सर ax static हो उसको suppose किए. Let us suppose if it moves at let us suppose even if you assume right now we will do it 0 because it's in static equilibrium. Okay, clear? So this is x bar in this case if it's a gravitational force. Understood? Okay, fine. Okay, now let us see. So that's how we have the gravitational force actually. So similarly, if you then this is per unit mass. If I write this equation, in this equation, this okay, so we'll see what is this equation later. So let us see here, if this is x, similarly you can have x, y, x, z and all. So basically my intention is to tell you this 2 will not come because this by 2 and by 2 is there. Okay, so 2 times of dou p by dou y divided by 2 will be there, so 2 gets cancelled. Okay, so some more question. I think Rohit, you have an issue. Basically here there are dy by 2 terms twice, so dy by 2 into 2, so 2 gets eliminated. Okay, in the calculation. Fine. So you can see carefully we have dou p by dou x minus dou p by, similarly minus dou p by dou x plus xx is equal to 0, minus dou p by dou y plus xy is equal to 0, and minus dou p by dou y, dou p by dou z plus xz is equal to 0 obviously. Okay, so this is what we have. Now clearly if I take this as unit volume, if gravity is the only force which is acting, if gravity is the only force which is acting actually, okay, so if gravity is the only force which is acting, then obviously x bar, if you compare with xxi plus xyz plus xzk actually, and you know actually this is how gravitational force will act, then can anyone tell me what are the values of this xx and xy components? Can anyone tell me what are the components of this xx and xy values actually? Come on, quick, fast. Can anyone tell me what is this xx and xy if gravity is acting only in the z direction? 0 obviously. Okay, so these two are zeros, so that means this is 0 and this is also 0. And what about xz actually? Xz is equal to minus rho g k cap obviously, so and xz component is minus rho z obviously. Okay, so this density is rho is nothing but density of the fluid obviously, because this is, whenever you are writing mass we write density of the fluid. Okay, so these equations get simplified as dou p by dou x is equal to 0, dou p by dou y is equal to 0, and dou p by dou z is equal to minus density of the fluid into g obviously. Okay, so these are the same equations which you see using hydrostatics, and in this equations you can see dou p by dou x is equal to 0. What is the meaning of that? Look, let me tell you. let us suppose, for example, you can have certain horizontal face for example. Okay, so let us suppose you have a horizontal face, and also you have some z axis from here. Okay, so let us suppose this is z, then this is x, and let us suppose if this is y, for example. Okay, x, y, and z. Now let us suppose if x direction along this plane is something like this, for example. Okay, so let us suppose if this is x and this is y, obviously this is z. Can anyone tell me if dou p by dou x is equal to 0, that tells you the variation of pressure in the x direction is 0, correct? If I take 2 points here on this plane which has same x coordinate, for example, if I call this point A and if I call this point B, what is the pressure difference between these 2 points? So gravity force per unit volume is called specific weight. Yes, of course. Okay, so rho g is actually called the specific weight. So this normally in case of fluids, this rho g is called specific weight. Okay, specific weight, obviously. Okay, weight per unit volume, like how you have extensive and intensive properties, similarly this is called weight per unit volume is called specific weight. That's it. Okay, so can anyone tell me what is the pressure difference between these 2 points A and B? Dou p by dou x is 0. That means if I choose 2 points along the same x, what is the pressure difference between those 2 points? Actually 0, obviously. Okay, so which means pressure at this point and at this point is also same. Similarly, dou p by dou y is also 0, which means let us suppose along a straight line, if I take a point B here and C here, can anyone tell me the pressure difference between these 2 points? That also 0, correct? This pressure difference between these 2 points is also 0, which means you can see the pressure at this point is same as pressure at this point, and pressure at B is same as pressure at C, which means if you take any point on a horizontal plane, the pressure is uniform at all the points. Yes or no? That's what we mean actually. Pressure difference in z direction only be there. So basically, if you take any horizontal plane in a static fluid, okay, in a static fluid only and only in a static fluid, if you take a plane, a horizontal plane, which is under the effect of only gravitational force. Okay, again there should not be any electromagnetic or ferromagnetic forces. So if you have only a horizontal plane in a static fluid in which only gravity is acting, then definitely pressure at any point in the horizontal plane will be same. Okay, so pressure is constant along a horizontal plane. Understood? So initially we don't know that pressure is only function of z, so we have assumed that pressure generally changes, but now you got some idea that this dou p by dou x and dou p by dou y is 0. That means these two implies pressure depends only on the vertical coordinate z, obviously. Okay, so if this pressure depends only on z, we see obviously dou p by dou z can be written as dp by dz. So dp by dz is equal to minus density of the fluid into g, which is same as minus specific weight, gamma, generally denoted with gamma of the fluid. Okay, so gamma is actually called the specific weight. Specific weight. Okay, so this is specific weight, of course, in this case. Clear? That's how we have this equation, obviously, which we use in all the calculations in general. Okay, so dou p by dou z is this. Now, why I am writing this in vector form is, you will see later in Navier Stokes and all, it will be helpful. See, grad p, I can write it as dou p by dou x I plus dou p by dou y z plus dou p by dou z k. Okay, and body force per unit mass, let us say for example, if x bar, if I write as per unit mass, then this is minus g k cap. Okay, where x bar is body force per unit mass. Per unit mass. Okay, so this is per unit mass, obviously. Okay, so minus g times of k cap, because for total mass it is mass into gravity, so for unit mass it is only g acting in the downward direction. So if that's the case, can I write, you know that dou p by dou x is 0, dou p by dou x is 0, and okay fine, dou p by dou x is 0, dou p by dou y is also 0, and dou p by dou z is equal to minus density of the fluid into gravity. Okay, so this is what we have. Can I segregate this equation as, if I write this as 0i plus 0j minus gk, for example, dou p by dou x minus 0, dou p by dou x minus 0 times I plus dou P by dou Y minus 0 Z plus dou P by dou Z minus then rho F into G obviously. Okay, so rho F into G. So let us say this is plus rho F into G, because minus of minus will become a plus actually here. So K cap is equal to 0. This we can write it as dou P by dou X plus dou P by dou Y I J K minus 0 I 0 J minus density of fluid into G K is equal to 0. Okay, now what I can do, I can delete this density here and I can write it as here, because these two are anyhow zeros. So density of into 0, density of into 0 minus 1. Okay, so this expression which is here is nothing but gradient of pressure minus density of the fluid into this vector. This is nothing but body force per unit mass. So this has to be 0 obviously. Okay, so very clear, this is per unit mass actually. Okay, so this x bar is actually for unit mass. Clear? Yeah, bye Sai Kumar, take care. Okay, yeah, did you all understand this equation, how we can write it in vector? Now why I am taking so much effect in writing in vectors is vector equations are independent of the coordinate system. Okay, like for example, you can see, let us suppose you have a velocity like this v for example. Okay, and you have x and also y direction like this. For example, if you resolve this vector in Cartesian system, you have this is y component of velocity, this is x component of velocity. For example, if I resolve that vector in, so obviously I'll write v is equal to vxi plus vyj obviously. Okay, and similarly, let us suppose if I resolve this in polar system, let us suppose if this is vr and if this is v theta for example. In that case, what we write as vr er cap plus v theta e theta cap actually. Now depending upon the coordinate system, these components will change. Yes or no? Means if you are writing in Cartesian, you will have vx vy. If you are writing in polar, you will have vr v theta. But in both the cases, is this vector v changing? But in both the cases, is this vector v changing actually? No, correct? Vector always remains the same vector, but depending upon your choice of comfort and your choice of coordinate system, definitely the component values will change obviously. Okay, so that's why writing equations in vector form is very useful, because any equation in vector form is valid in any coordinate system. Clear? The only thing is you should put gradient as per Cartesian or polar. That's it. Okay, clear to all of you? Like for example, gradient in Cartesian is what you know, all of you know this. In Cartesian we have dou by dou xi plus dou by dou by z plus dou by dou zk actually. Okay, and in case of polar we have dou by dou r er plus 1 by r dou by dou theta e theta plus dou by dou z ez. Okay, and spherical even I don't remember, because obviously we have to derive that. Okay, so but anyway, these two are actually helpful many times. If you want to apply this in Cartesian, you will take this expression for gradient. If you want to apply this in polar, you will take this expression for polar. That's it. Clear? But this equation remains same actually in both the cases. Okay, the main outlet is under influence of gravity. Under the influence of gravity, clearly. Okay, so under the influence of gravity, you can see a static fluid has pressure variation only in z direction. Okay, so this is only in z direction. Clear? So basically z is the upward direction is what we have taken. Okay, now so carefully if you see dou p or dp by dz, if I write, this is equal to minus density of the fluid into z obviously. Okay, now let us see certain cases in certain medium how pressure actually changes with respect to z actually. Okay, now let us using this is the hydrostatic equation obviously. Now pressure variations in certain fluids. in certain fluids. Okay, so pressure variations in certain fluids actually. First, let us suppose if you take incompressible fluid, for example. Okay, so incompressible fluid, like density is equal to constant. Okay, so density of the fluid is constant. Let us suppose you have certain static fluid, for example, and this is the z direction, for example. Okay, so this is z. Let us suppose this is 0, this is some height z0. At this particular point, let us suppose if the pressure is P, then at some other value of z, what is the pressure P at this particular location? Okay, so at this layer, what is the pressure P? At this layer, the pressure is P0. Okay, now if you try to simplify this, dP by dz is equal to minus density of the fluid into g. So dP by dz is equal to, or dP is equal to minus rho f g dz. Now it is in variable separable form clearly, and this is a constant, g is also constant. So if you integrate, obviously if you integrate, you know at z is equal to z0. Okay, so let us suppose at z is equal to z0, pressure is equal to P0. At some z, let us suppose at z equal to some other location, the pressure is P. So if you integrate, you will see P minus P0 is equal to minus O F G Z minus Z0. So clearly you can see this is a linear equation. This is of the form y is equal to mx plus c. Obviously this is a constant, so Z0 is a constant. So this is actually a linear equation. So in case of constant density or incompressible fluids, let us suppose if this is P0 and if this is P, clearly as you go down, pressure increases. So this variation which connects these two is actually a linear variation. Okay, so this is linear. That's why next, when we solve questions of hydrostatics and all, in case of hydrostatic forces on plane surfaces, we actually draw linear variation of pressure, because we practically treat liquids as incompressible because density is constant actually. Okay, so therefore this is the variation. Similarly, if you take compressible isothermal fluid, for example, compressible fluid at isothermal conditions. Let us suppose, for example, if there is some ideal gas. Okay, isothermal. Let us do the analysis much simple. Let us suppose if this is ideal gas actually. Ideal gas. Okay, so you know dP by dz is equal to minus density of the fluid into g. Now again you take the coordinate system. Let us suppose if this is z direction, for example, and let us suppose there is gas all over. Okay, so there is a gas. Clearly this is an ideal gas, but is in static condition approximately. This as a bulk, it is not flowing anywhere. Obviously the microscopic movement will be there, but there is no macroscopic flow of gas at any location. Now clearly if this is Z0, if the pressure is P0 at this point, and at some location Z, if the pressure is P, for example, what is the variation of the pressure actually? So if you see that, let us suppose if you take an ideal gas, you know P is equal to rho RT. So density is equal to P by RT obviously. Okay, so you can write this dP by dz is equal to minus P by RT into G obviously. Okay, then you can do one thing, you cut this guy and put it here, and you cut this guy and write it here. So 1 by P dP is equal to minus G by RT dz actually. Okay, so this if you integrate again, at z is equal to z0, pressure is P0, and at z is equal to z, pressure is P, for example. If you do this integration, integration of 1 by P is log P minus log P0. So log P by P0, log A minus log B is log A by B. So this gives you ln P by P0 is equal to, now this T is constant because we have made this assumption, it is isothermal. So minus G by RT times Z minus Z0 actually here. Okay, so this implies P is equal to P0 into exponential of this minus G by RT into Z minus Z0 actually here. Okay, means you can clearly understand with respect to Z, pressure varies exponentially. Pressure varies exponentially. Clear? And you can understand, so this is pressure varies exponentially in case of a isothermal fluid, but of course it's a ideal gas. Okay, because we have used the ideal gas equation, so obviously the variation is exponential. You may have a doubt like why I have drawn only curve like this but not like this. Okay, because you can see this dP by dz value is equal to F by Z, and if you write this O as P by RT, one thing you know, as this Z decreases, pressure increases, so that's why as z decreases, this pressure should actually increase obviously, so the slope should be increasing in the downward direction. Clear? So because of that particular reason, I have drawn a curve which is like that. Okay, it's exponential. Is this clear to all of you till this point? Okay, so please type in the chat box, is this clear to all of you till this point? Come on guys, quick. Okay, you can see simple integration, if you perform, you can see it is exponential in relation. Okay, next, if you take non-isothermal compressible fluid for example, and this question I think is actually a previous year GATE question. Okay, in 2016 when IISc has organized GATE, it has given this. Then non-isothermal compressible fluid. Non-isothermal compressible fluid means where temperature is not constant. Let us suppose if you take the case of atmosphere for example. Atmosphere, this is T0 minus alpha times Z. As you go up, temperature generally decreases. This alpha is called lapse rate, of course, which is minus, okay, since I have taken minus sign obviously, so 6.5 Kelvin per kilometer, means for every 1 kilometer ascent you experience a temperature drop of 6.5 Kelvin roughly. Now if you integrate this again, okay, so dP by dz is equal to minus g density of the fluid into gravity. Okay, so this is what you have obviously. So if this is a compressible fluid, let us suppose if you treat air as ideal gas, again ideal gas obviously, so dP by dz is equal to minus p by RT, but this time t is not constant, it is function of z actually, into g of course. Okay, so g. Now clearly if you again do the same thing, this p comes here and this d goes here, then integral dP by p within the limits, okay, is equal to g minus g by r integral 1 by T0 minus alpha z dz actually here. Okay, so you can clearly see this is at z is equal to z0, p is equal to p0, and at z the pressure is p. So if you simplify, we get, you know, p ln p by p0 obviously is equal to minus g by r into 1 by minus alpha, obviously the inner derivative, ln T0 minus alpha z naught actually. Okay, so T0 minus alpha z by T0 minus alpha z naught obviously. Okay, so this is anyhow constant, so this minus and this minus gets cancelled. So basically p is equal to p by p0 into exponential of, okay, so okay, this g by r alpha, if you write it on the top for example, okay, so this total quantity you can bring onto the top of the logarithm, g by r alpha. So obviously this p by p0 or p0 is equal to p0 times ln log will not be there because we eliminate log on both sides. So this is T0 minus alpha z by T0 minus alpha z naught power g by r alpha actually. Okay, means basically you can see this is some constant. So with respect to this z, this pressure changes as per some power. Okay, so this is called power law kind variation. Okay, so in case of a non-isothermal case, the pressure and z changes as per this power law kind of variation, because as z increases, p changes with respect to some power of z actually. Clear? So these three things are a bit of importance in day-to-day case. So are you all clear with these points? So please type in the chat box. Okay, come on, quick. Simple thing, the using hydrostatic law we are deriving a lot of important things, that's it. Okay, so let's continue now. So obviously you know that yeah, pressure is measured with respect to both cases. One is absolute zero and the other is atmosphere reference. So this is called gauge pressures obviously, or vacuum pressures, and these are called absolute pressures. Okay, these are called absolute pressures, obviously. Okay, now whenever you take this, like for example, you take this is the curve for pressure. Obviously, atmosphere is at some value which is 101 kilopascals roughly. Okay, this is the atmosphere in general, in standard case. Okay, now when this is 101.35, let us suppose if you take a pressure which is more than atmosphere, then when you measure this with respect to absolute zero, this is called absolute pressure. When you measure this gap, then definitely this is called P gauge. Similarly, if you have one more pressure which is like this, then clearly when you measure this with respect to absolute zero, this is called P absolute in case of vacuum, and from atmosphere this gap is called P vacuum pressures. Okay, so and you know the equations, obviously. In case of gauge pressures, P absolute is equal to P ATM plus P gauge. In case of vacuum pressures, P absolute is equal to P ATM minus P vacuum. Okay, so simple lengths, if you do subtraction, you will get. And how this 101.35 is coming, basically we'll see pressure measurement devices. Pressure measurement devices. So obviously the first simple thing that you know is barometer to measure atmospheric pressure. Like normally this definition of 76 centimeters of mercury comes out from this actually. Okay, if you see, for example, if you take mercury in this, and obviously if you fill another tube of mercury, and if you invert in this, for example, okay, so let us suppose if you invert this, then you will see there is an elevation of 76 centimeters on an average at atmospheric, and of course this experiment is done locally, so at that particular point they have standardized this. Okay, so 76 centimeters of mercury head actually. Okay, now the main question is why they have chosen mercury actually. Okay, so this is actually the important question, and for this question our hydrostatic equation gives the answer. Okay, look, definitely if this fluid is in static condition, the pressure at this point and at this point at every point on this horizontal layer should be same actually. Okay, now if this is the condition, in case of incompressible fluids, you have studied one thing, the pressure difference between these two, P and P naught, is actually, if you delete this minus sign, this can be written as Z naught minus Z, obviously, which means if you know this gap Z naught minus Z, then pressure difference between these 2 points can be calculated directly just by multiplying specific weight. Okay, now coming to that, if you take the pressure at this point 1 and also at this point 2, then definitely P2 is equal to P1 plus density of mercury into Z into that 76 centimeters, whatever you call it, H for example sometime. Okay, so this is the equation as per hydrostatic law, correct? The pressure difference between these two is actually because of this. Now why only mercury is taken is because the pressure at location 1, actually to exactly measure the effect of this, in this portion whatever you have, the pressure which is present at that point should be very low, and this pressure is called vacuum pressure, obviously, VACUUM pressure. And mercury is one such substance which is having very low vapor pressure. The reason for that is, you know, evaporation condition. Normally what is evaporation? Let us suppose if you pour some liquid here, then with air or generally these particles which are in the liquid gets evaporated because of the evaporation mechanism. Now if you see, because of mercury being a very high density molecule, the evaporation is actually very difficult in case of mercury, which means when you keep mercury like this, the amount of mercury vapors present in this region is very less, and if mercury vapors are very less, then definitely the pressure exerted by the vapors will also be very less actually. Okay, yeah, high question, all these things are consequences of because of very high density molecules. Okay, so obviously it has less vapor pressure, clear? It has very strong cohesion, and evaporation becomes very difficult because evaporation phenomena cannot lift very high density molecules, obviously. Okay, so that's what we have, and because of being high density, that vapor pressure is actually 0, which means if you take this exactly 0, P2 is equal to density of mercury around 13,598, 13,595, sometimes we can take 9.81. Again, it is also subjective to poles or equator, and that's 76 centimeters, so 0.67. So if you do all these calculations, roughly you will end up with 1. 101.325 kilopascals in general. Okay, that's how 1 atmosphere is actually taken as 76 centimeters of mercury, or 76 centimeters means 760 mm of Hg. And if you do this calculation, roughly the answer will be 101.325 kilopascals, and sometimes you write this in bar as 1.01325 bars. Okay, so and 1 bar is equal to 100 kilopascals. Okay, so all these are the diamond measuring of pressure actually. Okay, so why we take PATM 0? We have never taken PATM 0, no? This P2 is actually PATM. This is the vapor pressure inside the glass tube. Okay, clear? Actually, whatever we have taken here, that's vapor pressure. Vapor pressure is actually 0, not the atmospheric pressure. Got it? Clear? Now, so there are certain techniques to measure depending on hydrostatics. The first is piezometer. So piezometer is actually a very simple construction. Let us suppose if you have a pipe in which some fluid is flowing. Okay, and here the pressure is actually P. Now if you connect some tube, actually if you puncture this tube and if you connect this glass, for example, so let us suppose if you puncture this tube, for example, okay, if you puncture this tube slightly and if you connect this pipe, then definitely what happens? Here the pressure is high, here the pressure is low, so obviously some fluid will try to come to up to certain limit actually. Okay, so let us suppose if this height is h, for example, okay, and here the atmosphere is PATM in general, local conditions, the location in which you are doing this experimentation. So this is h. Now as per hydrostatics law, you can see, since this particular set of fluid will be in static condition, the pressure at this location and at this location should be same. Okay, so this, if you call this 1 and 2, P1 should be same as P2. So P1 is equal to PATM local plus density of flow into G into H, obviously. Okay, so density of the fluid. So let us suppose in actual practice, here this fluid is roughly approximately in static condition in this direction. Okay, in this direction, let us suppose there is no effective motion of the fluid particles, then this is what you have. So P atmosphere, you know, H you can measure from this scale. Let us suppose you take a scale and you can measure. So rho F into G is also known to you, okay, because you know the density of this fluid and gravity is 9.81. So that's how P1 can be calculated actually. So this is the first simple construction. For gauge pressure, why PATM is 0? Because we measure with respect to gauge. Like for example, see, P gauge is equal to P absolute minus PATM local. Okay, that's what we are measuring with respect to atmosphere. Clear? That's why this PATM gets subtracted. It's not 0. Okay, normally cannot make this 0. 101.358 hour. Because density of mercury can slightly be changing. Okay, it's not like exactly 598. It's in decimals actually. Okay, but the main idea is 101.3 roughly is the 101.3 kilopascals around is the standard value. Okay, now, so because of this, since we are measuring this PATM, we are subtracting, that gets eliminated. It's not like PATM is 0. Okay, PATM is never 0. Understood? Because obviously there is atmosphere. If there is no atmosphere, we all will die. You know that? Do you know if you don't have atmosphere, what happens? If you don't have atmosphere, then do you know what happens actually? Do you know what happens if you don't have atmospheric pressure? Will burst like nothing. Yes, exactly. Okay, if you see, normally blood flows. Okay, if you ever visited doctors, they'll generally write this blood pressure BP as 120/80. They'll tell you this, you know, yeah, due to pressure difference, obviously. Normally if you ever go to any doctor, normally if they check your blood pressure BP, the normal ideal condition should be like 120/80. This is called the systolic and this is called the diastolic pressures actually. Okay, now what is this 120/80 actually? Any idea? What is 120 and what is 8? Let us suppose they have two numbers. What does these two numbers actually mean? Our body burst. Basically if you see, this is actually 120/80 is actually 120 mm of Hg or 80 mm of Hg. And this is actually gauge pressures. Gauge pressures. Okay. Now actually if you see, ATM is 1 second is our pressure. No, both are actually our pressures only. Okay, so it is 120 and 80. So basically this mm of Hg, if you measure this pressure as per this understanding again, OFGH, you will get what is the actual pressure in kilopascals and all. Now if you see those are gauge pressures, means always the pressure inside our body is more as compared to the atmospheric pressure. Means let us suppose if I take, for example, let us suppose if I take my hand, okay, at some location. If I take my hand like this, then definitely the pressure at this acting on the surface from outside is atmosphere, but inside I have a pressure which is more than atmosphere. But why blood do not come out generally is this pressure balance is maintained by this skin actually. Okay, like for example, let us suppose you take a sponge, for example. Okay, you dip the sponge in water and you take it out, for example. Okay, you know clearly density of air is less, very much less, thousands of times less as compared to density of water. Okay, but still the sponge has the capacity to hold water because of the pore size actually. Yes or no? Similarly, coming to the blood configuration, this skin has the configuration to hold the blood and to maintain the pressure difference actually. Means this system will not allow the blood molecules to come out because of the pressure difference due to 760 mm and 120 mm. Okay, but when you go to high altitudes, like for example you are going for a trekking, okay, mountain trekking for example, then what happens, you know, as Z increases your pressure decreases. Okay, so when Z is increasing and your pressure is decreasing, inside 120 will be still 120, I mean gauge, but outside it won't be 760, it starts falling. Yes or no? So there comes certain pressure difference around some 600 or 650. You can see there comes certain pressure difference where this skin or this sponge actually cannot hold that particular pressure difference. Okay, so then in such case what happens, obviously blood, even now blood molecules are trying to come out of this pores, but this atmospheric of 760 is actually balancing them. But when you go to the top, because of the decrease in this pressure, the pressure inside is actually definitely more, so obviously blood starts coming out of your skin. Okay, looking at the weak points, it looks for certain weak points, like how a material fails. Similarly, it looks for certain weak points actually, and blood starts coming out of that particular pores in the first attempt. Okay, and obviously then after it propagates to its surroundings actually. Likewise, if you see, there is some phenomena called nasal bleeding actually. Nasal bleeding. Okay, like when you go to high altitudes, generally the pressure outside will actually fall so much, and whenever you enter, obviously the nasal vessels are very weak in this particular region. Normally it's a common thing, you know, if you want to punch someone, the first place that you punch is nose, correct? Because obviously here the vessels are very weak actually, and yes, naak se खून आएगा, ठीक है? And so whenever you go to the top, obviously when pressure is decreasing because of the high blood pressure is common at every point in the body, so the first bleeding point that you can generally see is the nose point. Okay, normally I can anyone who is scared of blood, I can show you just some small amount of blood actually if you want, like nasal bleeding during trekking, you can see. So images, like for example you can see this blood actually starts falling normally in case of trekkings and all, so that's very dangerous phenomena actually. Okay, clear? Practicals होना चाहिए ना? How do you know that this is gauge pressure? 120 mm of Hg is gauge. How do you know this? Any idea? Obviously it's not, finally the main essence of education is to develop new devices. Okay, it's not like you keep on writing P plus OGH is equal to this mathematical stuff is helpful to some extent. Okay, even I love maths, I teach maths, but the main importance of physics is to apply it to new devices. Okay, and try to get something out of it. How do we know that 120 mm of Hg? Practically noted values. अच्छा ठीक है, प्रैक्टिकली सिर्फ mercury का रीडिंग मिलता है. ओके, सो लेकिन वो mercury का रीडिंग से हमें थोड़ा सा कैलकुलेशंस करना पड़ेगा प्रेशर कैलकुलेट करने के लिए. लेकिन कैसे पता है कि ये मतलब ये एब्सोल्यूट प्रेशर और गेज प्रेशर, दिस इज एक्चुअली गेज. ओके, सो गेज कैसे पता है? नॉर्मली आज तक क्या हुआ, मार्केट में ये डिजिटल प्रेशर मेजरमेंट डिवाइसेस आया. ओके, बट लेकिन आपने अगर पुराना दिन देखा तो normally you'll see if you go to doctor, what he do is he will actually tie one, he put one belt like this to your shoulder at this point, ask you to tight your fist, then tight this, and he will start pressing one, small, what do you say, that is like a small bulb kind of thing. Okay, so a bulb he starts pressing, and you can see the mercury actually increases. You have seen this device. Normally if you go for blood test, generally in olden days, right now there are a lot of digital meters based on electronic sensors, but in olden days you see he put a tight band here and he actually start pressing one rubber balloon. Okay, and slowly the mercury column will actually increase. Correct? You might have seen this. So the name of that device is actually called sphygmomanometer. Okay, it is basically a manometer, and this is used for measuring blood pressure. So I'll show you again that also. Sphygmomanometer. I think I missed H here. I am very little poor in English, so you can forgive me for that. Yeah, this is what you might have seen. Okay, you see here these guys. Yeah, I think this is a perfect example. Yeah, any one image if you open in general. Oh, this is directing to Amazon. Fine. Let us see some normal picture. Yeah, fine. Okay, so let us suppose you see this. Why nothing is opening? All these are for sale, I guess. Okay, so anyway, fine. You can see somewhere at any point actually like this. Now how do you know this is actually gauge pressure? Is because mercury will actually rise, but have you ever observed this opening? If you see generally very closely, this glass tube will be open to atmosphere here. Understood? This glass tube in which the mercury rises, this will be actually open to atmosphere. You can see. Normally if you open this sphygmomanometer, you can clearly see the top of the glass tube will be open. It's not closed. So obviously this measurement is PATM plus this. Okay, and the scale readings is set in such a way, they have already calculated and they have identified that this much height of mercury corresponds to 120 mm of Hg. That's why in the sphygmomanometer, normally if you see, you have the pressure readings obviously in terms of mm of Hg, which you definitely know. So that's why the doctor says, your BP thoda high hai, 130/40, so you have to take these medicines and all, because this is how you actually measure the pressure using this particular hydrostatic techniques. Clear to all of you? Okay, now anyway, you can see, now coming to this, this is basically a device to measure blood pressure. Fluid mechanics, solid mechanics, all these things are really one very important applications actually. Okay, 120/80 is normal. Okay, yeah, 120/80 is normal. Okay, so normally if you try to understand one thing to measure this blood pressure, normally if you take human body for example, okay, so in case of human body, blood सुन कैसी दर्द करता है sorry. Okay, fine, I won't talk about the blood again. So normally if you see the human body, this mechanics is playing a very important role. Okay, let us suppose you have some veins for example. Okay, so in veins definitely blood flow at certain velocity, which is flow through pipes. Okay, so and you all know we all have a pump in our body. Okay, we know there is a pump. Okay, so pump, what is the job of the pump? To supply some energy and increase the things actually. That actually creates pressure difference. Okay, pressing the bulb actually creates the pressure difference and eases the flow of mercury. That's it. Bulb pressing is actually for, normally have a mercury bulb at the bottom reservoir, so that this bulb is actually connected to the pressure variation by the doctor, and that helps in flow of mercury. That's it. Okay, so normally if you see, we have a pump in our body, and obviously let us suppose you have a fracture, then definitely they'll put steel plates and all. So again, some solid mechanics will comes into picture there, and lot of fluid heat management. Let us suppose in winters we put jerkin, okay, like this. Like in summer we don't put. Why? Because we actually experience a lot of heat transfer mechanisms, because of which we feel the human comfort. So everything, if you study like this, definitely there is no need of remembering anything. Okay, things will go fine. But anyway, come on, let's get back, time is running up. So this is piezometer, one of the common construction, and it's also a very simple construction. The reason is just you have this bulb, or just you have this manometer in particular. Okay, so you have this particular simple glass tube. Using this simple glass tube, you can measure the pressure. So this construction is very simple, but लेकिन इसमें बहुत सारे problems भी है. Okay, so the first problem is, if you see the defects of this actually cannot measure high pressure. Okay, can't measure can't measure very high pressures. This cannot measure very high pressures. Why? Because you can see in general, if this pressure is actually very high, this height of mercury going up will also be very high, correct? If you want to have a high column of mercury, that means the glass tube should be of very high. Okay, so that means maintaining a very large length of glass tube is practically very difficult. Let us suppose if I can measure pressure only up to few kilopascals, okay, but let us suppose if it goes beyond that, this glass tube size keep on increasing, and maintaining such a big glass tube is actually very less. Okay, clear? And also one more thing, let us suppose if this pressure is less than atmospheric pressure, then this device is no more in use. Yes or no? Because when pressure here is less than PATM, definitely instead of this fluid coming into this column, what happens in reverse, air will actually flow into that fluid. Like for example, when you are making molds and all for doing castings, you can see the pressure will actually seep, means the atmospheric air will actually seep into the mold. Yes or no? And obviously similarly here seeping happens, and obviously you cannot find any liquid column to find the pressure, obviously. Okay, third case is, let us suppose instead of liquid if I have gas, can I use this device? Instead of liquid, let us suppose if there is some gas flowing in a pipe, then can I use this to calculate pressure? As soon as you puncture, gas will escape through the tube, that's it. Okay, so like this, there are many defects in this particular piezometer, so that's why this piezometer came into existence and very soon it left out because of its disadvantages. Okay, now from here, what are the defects in this? If there is a gas, definitely, then one thing that you can understand is this gas should not escape out of these tubes. Okay, so that means there should be some restriction here. Yes or no? And also, even for high pressures, there should be some reference about which you can actually measure the pressure difference. So if you see, that gave us to the situation of U-tube manometers. In U-tube manometers, what we have done is actually you have a pipe, and this time this pipe was made slight change like this. This pipe was made to some small change like this. Okay, and what we have done here is we have kept some mercury actually in this case. This is mercury, and this fluid, it need not be always mercury. This is called manometric fluid in general. Okay, because sometimes when measuring gas pressures, it can be any oil also. Okay, so this is manometric fluid of density rho m actually here. Okay, so this is manometric fluid of density rho m actually in this case. Okay, now if this is manometric fluid, hey, what is the time? 8:53. Oh my god. Okay, see here. But are you all understanding the things? Because okay, fine, I can cover at some locations where mathematical equations are there. I will not dare the mathematical equations, but are you all understanding the concepts clearly? As long as you understand the concepts, because I understand this is the final time you're learning fluid mechanics before you get examination. I know this. So that's why even I'm spending some time to make you understand certain important things. Okay, fine. Because I have also promised you in the short that along with mechanical, I'm trying to cover the XC part also. Okay, so guys, I actually have a thing to say to all of you. Normally in YouTube English channel, okay, so yeah, English Gate Wallah English channel, YouTube English channel. Like because so please go on the same speed, don't increase the speed. Okay, okay, fine. Mohit, I don't increase the speed, fine. But I want you to do two things actually. Whatever the XC I have promised you, for that the actually जो important videos होता है, मतलब जब मैंने वो पेड कोर्स पढ़ाया था, कॉम्प्रिहेंसिव कोर्स, कंप्लीट मतलब डिटेल्ड कोर्स ऑन फ्लूइड मैकेनिक्स पढ़ाया था, सो उस टाइम पे जो इंपॉर्टेंट टॉपिक्स होता है एक्सी के लिए, मान लो कि वो कंट्रोल वॉल्यूम एनालिसिस में बहुत लोगों को दिक्कत होता है कि सर एंगुलर मोमेंटम, जब एंगुलर मोमेंटम का क्वेश्चन सॉल्व करते हैं, वेलोसिटी को पॉजिटिव लेना है या नेगेटिव लेना है. Okay, so there are many questions like this. Okay, so to eliminate all these questions, in Gate Wallah English channel we are uploading the paid batch lectures, means the comprehensive course lectures of control volume analysis and potential flow. Okay, so you can go through that. Okay, so because when I'm teaching that, I'll just refer you one day before that, please go through that videos, so next day it will be effective for us to solve all the problems actually in a single attempts. Okay, so please do that, and I'll try to post some more videos regarding boundary layers and all where we have certain nice concepts. Okay, we will talk about that. Okay, fine. Anyway, so this is the manometric fluid. Okay, now let us suppose if you have some fluid here. So this is P, obviously. Okay, and so seriously, if you see, this is the deflection, for example H here, and here we have P ATM local. Then clearly we can write P plus, for example, if this is X, okay, then P plus rho fluid G X plus H. So this is the pressure at this point. Similarly, since this is a static fluid, you can see the pressure at this point 1 and at this point 2. Okay, so pressure at point 1 and pressure at point 2 is same. So P plus rho F G X plus H is same as P ATM local plus rho manometric fluid G H is what the equation. Okay, so in this equation, everything you know, you can measure X H with the help of a scale. You know P ATM, you know density of the manometric fluid, you know density of the fluid which is flowing in this, so you can calculate what is this P actually. Okay, that's what you have. Yes, my lectures. Okay, the lectures what I have taught you. Okay, yeah, I mean not to you directly, to some of the students of PW. Okay, now let us see here. So this is P ATM local, that's P. So this is X and this is H actually, and this is the manometric fluid. Okay, so this is what you have as P, obviously. Now many times the main point of interest is, rather than measuring pressure at a point in a pipe, let us suppose if there is a flow happening in a pipe, the main point of interest is identifying the pressure difference between 2 points, correct? So many times, more than calculating pressure at a particular point, you have to calculate the pressure difference between 2 points. Okay, so how you can do that? Just instead of leaving this to atmosphere, what you can do is connect one more pipe. That's it. Okay, so then this deflection actually gives you the pressure difference between the 2 pipes actually. Okay, so that's what we can do. But anyway, right now I'm just keeping this. Now the story of inclined tube manometers is important, because from this, the next step they felt is inclined tube manometers. Inclined tube manometers. So see here, in the first step, they were able to measure only certain pressure range of a particular incompressible fluids or basically liquids. But this device is not suitable for gases and all, but they eliminated all these problems in this case. Okay, like for example, even if you put a gas, this mercury will not allow the gas to escape, so you can measure the pressure difference. This can even measure high pressures, because even a small deflection in mercury can also measure high pressures. Yes or no? Because if this is increasing, look, for a given pressure, everything is same. Let us suppose if you increase this, this can be decreased, means these tubes can be designed in such a way that if you put high density fluid here as manometric fluid, this H can be even small for calculating the pressure difference actually. Okay, multi-fluid manometers ka characteristics bataiye sir. Yes, I'll teach you. Okay, no issue. So see here, I'll tell you this inclined tube manometers. Why this inclined tube manometers came into picture is, the main problems here are this, and here using this device you have eliminated all those problems. Now once you can measure the pressure of gas, liquid, maybe gauge pressure, vacuum pressure, everything. Now the next point is to increase the accuracy in the pressure measurement. Okay, now let me ask you one question. Let us suppose if I ask you to measure 5 centimeters length and also 50 centimeters length, or 10 centimeters for example, let us say 8 centimeters length for example. In which case your measurement you can measure more accurately? Let us suppose I asked you to measure 5 centimeters and also I have asked you to measure some 8 centimeters length. In which case your reading is most accurate? In which case your reading is actually most accurate? Obviously 8 centimeters, correct? Because as a human we may commit some mistake of 0.1 mm for example, but coming to this 0.1 mm, the 0.1 mm difference here and here, compared, if you compare the effect of this 0.1 mm mistake in this 8 centimeters is neglected, because the percentage error will actually reduce. Means one thing is very clear, if there is a high length we can actually measure it very effectively, and let us suppose if you are measuring very small length, even though the small mistake we make, it creates a lot of error. Okay, so that's why what they decided was, instead of taking this H, if we can somehow increase this H, like measurement of this particular value, it can be done in some other way which increases accuracy, then definitely pressure can be calculated in an effective way actually. Okay, now if you can understand this, see, the main technique here was taking the difference between these 2 points and calculating the pressure difference between these two. Since this fluid is in static condition, let us suppose if you take a static fluid for example, this is 0.1, this is 0.2, this is H obviously. Okay, but let us suppose if you take a horizontal point here, see, Definitely P2 is equal to P3 because this fluid is in static condition, yes or no? But what is this length actually? Let us suppose if this length is L, and let us suppose if this is theta for example, then L is equal to H by sine theta, or L is equal to H into 1 by sine theta actually. Okay, so we can write this. But if you see, the pressure difference between this point and this point is same as pressure difference between 1 and 3, obviously, because there is no variation in pressure between these two. Okay, so to measure this particular pressure difference over this height, instead of measuring this H, if you measure this L and if you multiply it with sine theta, then definitely you can get the same analysis again. Like for example, P1 minus P2 is equal to rho FGH, which is same as rho FGL sine theta. Correct? But you know one thing, measuring this L is highly accurate as compared to this measuring H, obviously. Okay, theta you anyhow know, you can just take an angle and you can put sine theta, obviously. Now this is the concept of the idea behind inclined tube manometers. Okay, so to measure the effectiveness or to measure the accuracy in pressure measurement, rather than doing straight distances, if you do this inclined distance, it would be helpful for you. Okay, so that's what we have. So rho FGL sine theta, and L is equal to H times of 1 by sine theta actually. And clearly you can see, whenever you change a small pressure corresponding to a difference of H, the deflection will increase by this factor, and this factor is called sensitivity factor. Sensitivity factor, because the sensitivity of the deflection depends on this guy. For a pressure difference equivalent to H, the actual deflection that you will see in the manometer is H into 1 by sine theta. So the deflection can be increased, because of which you can measure the pressure highly accurately. So this is the concept of inclined tube manometers, where you actually, instead of keeping this limb straight, you will actually incline it at some angle theta. That's it. Understood? Clear? Did you all understand this? Everyone? Certain logics has to be understood. Okay, if logics are understandable, then things are pretty much simple to work with. Now let me go to one last case of differential tube manometers. Anyhow, basically just instead of this leaving this open, you connect it to some other pipe, okay, at some other location. Then inverted tube manometers. Inverted tube manometers. Okay, so what about this inverted tube manometers? See here. Why inverted tube? You might have studied this statement. Inverted tube manometers. Inverted tube manometers are more accurate than U-tube manometers. U-tube means, of course, differential. U-tube manometers. Have you seen this statement anywhere? Do you know this? That inverted tube manometers will actually give you better accuracy. Come on, Kishore, Chinmay, Subhash, Mudit, Ladani, Ranjit, Shubham, all of you. Kalyani. Have you seen this statement anywhere? No? Come on, quick. Please type in the chat box fast. You might have seen this. No, yes, no, yes, no, no, no. Okay, fine. Fine. Out of the people who know, how many of you know why it happens? How many of you know why it happens actually? Use it for low pressure difference. Why low pressure difference can be measured effectively using inverted tube, which is not possible with U-tube? This is my question. Then. Okay, fine. I'll explain you. Let's not spend too much time. Guys, I'll tell you why this happens. This happens because of, again, the same logic. The reason is, see, I will explain you with the help of a simple, pipeline. Let us suppose you have a pipeline actually like this. Okay. Let us suppose you have a pipeline actually like this. Now let us puncture this guy at two locations. Okay. So if you puncture this, let us see. Okay, so let us suppose you have this. This is U-tube straight away, and this is inverted. Okay, and let us suppose if some fluid is flowing in this pipe, for example, and here you have mercury, for example. This is H deflection, or this is X, for example, and here you have mercury. Okay, so some manometric fluid, and this is fluid actually. Okay, this is the actual density of the fluid which is flowing. Similarly, here you can see there is a deflection of Y actually, and let us suppose here also there is certain manometric fluid. So let us call rho m inverted, for example. Okay, and this is rho m manometric fluid density. Now you can understand one thing. If you apply the pressure balance here at this point, clearly if you measure the pressure difference between these 2 points using this manometer, you take the datum 1, okay, A, B, for example. Okay, so this is A, B clearly. Okay, and this is 1, 2 obviously. Okay, so this is A, B. Can I say if you call this length, okay, as for example, for example A, let us say small a. Okay, so let us suppose if there is no variation of pressure in general, so between in the y direction to small extent, okay, because this pipe is very narrow pipe in general. So can I say P1 plus rho f g times of A plus H is equal to, sorry, A plus X is equal to P2 plus rho f g A plus rho manometric g x actually. Can I say this, yes or no? If I apply hydrostatic equation, pressure at this point is nothing but pressure at this location plus this column. Similarly, pressure at this point is nothing but pressure at this location 2 plus this fluid column plus this manometric fluid column. So can I write that equation, yes or no? Come on, quick guys, time is running up, please fast, reply fast. Okay, so can I do this? Yes. So obviously you can do one thing, this A and this term gets cancelled, so P1 minus P2 is equal to density of manometric minus density of the fluid times Gx actually. Okay, so this is Gx obviously. Now let us understand one more thing. If you again measure the same pressure difference using this inverted tube manometer, let us suppose if this is B, for example, what you can write is, again if you take the difference here as points C and D, for example, then P1 minus density of the fluid into G into B plus Y is same as P2 minus density of fluid G into B minus density of manometric in inverted tube into G into Y. This is the equation, correct? Can I write that equation? Because if you take the top manometer, definitely pressure at this location is pressure at this location minus this fluid column. Similarly, pressure at location D is pressure at this location minus this fluid column minus this fluid column. That's what you have. Okay, now if you do certain simplification, again this B and this term gets cancelled. P1 minus P2 again in this case is rho fluid minus rho manometric inverted Gy actually. Okay, you can observe one thing, this is not manometric minus fluid but fluid minus manometric, because let us suppose if this is density of the fluid which is flowing, this is manometric fluid density in the inverted tube. Clearly in inverted tube manometers, manometric fluid is lying on the top of the flowing fluid. That means this density should be definitely less as compared to this density. Yes or no? You cannot use mercury here, because if you use mercury, this mercury will land in this tube and obviously it blocks the pipe. That's it. It won't act as a manometer. Then it just acts as a bypass for the flow. That's it. Understood? So in case of inverted tube manometers, definitely this density should be less as compared to this density in order to use the in order to maintain the purpose of a manometer. Okay, so that's why in inverted tubes, density of the manometric fluid is actually less than the density of the flowing fluid, whereas here the case is different. Density of manometric fluid is greater than the density of the fluid. That's why the pressure difference is got in terms of this manometric minus fluid, but here when you use inverted tube manometer, fluid minus manometric. Did you understand this difference clearly? Physically also this has to be less because of this gravity. Clear? And normally the substance that we use here is compressed air. Compressed air is what you use generally here. Okay, now tell me one thing, but still not getting accuracy reason. 1 minute. Okay, just 1 minute. See here, you calculate this P1 minus P2 using this or using this, the value should be same. Yes or no? Why it is more accuracy? Just a minute. Okay, it will get cleared. So please tell me, in this case the pressure difference P1 minus P2, whether you use whether you calculate using this manometer or this manometer, it should be same because it's the same pipeline. Okay, so that means, can anyone tell me, if P1 minus P2 is same in both the cases, density of manometer fluid minus this into Gx should be same as this guy, density of fluid minus rho manometric I Gy actually. Okay, G gets cancelled. Now clearly one thing you can observe is x times of rho manometric minus rho fluid is equal to y times of rho fluid minus rho mi. X and y are the deflections of mercury levels or manometric fluid levels in U tube and also inverted tube. Now try to understand. Let us suppose if, for example, if you see this value is generally rho m minus rho f is generally very large as compared to, or at least large as compared to rho f minus rho mi, because normally in case of U tube manometers this fluid is mercury, okay, 13,600. Let us suppose for example water is flowing, compressed air maximum 1.5 kg or 1.3 itself, okay, not even going to 1.4, let us say kg per meter cube. This value is something around 998, this value is around 12,600. So you see this is 12 times more, okay, so this value is actually 12 times more than this value. That means clearly y is greater than x. Understood? Okay, y will be more than x. And also some of you have commented that even inverted tube manometers can be used for low pressure defense. The reason is this, okay, because here if you try to measure very low pressure defense, because of this high value the deflection what you see will be very small actually. But if you use this inverted tube manometer, this deflection will be almost like 5 to 6 times of that particular x, so you can easily measure the deflection and you can calculate low pressures very easily. Understood? Clear? So that's why inverted tube manometers are used for even measuring very low pressures in general, and also the accuracy is very high, but maintaining it is difficult because of this, okay, compressed air. Managing this is not very easy because normally in actual case what you have is you will have a valve here and this valve is connected to a supply of compressed air. Again you need a compressor, all these things. That's why in your college labs you will see only this but not this in general because it's costly. Okay, I guess many of you might not have seen inverted tube manometers till now, because in case of inverted tube manometers definitely maintaining the compressed air and valve is very high, is very effective actually. Okay, even this inverted tube manometer is very much useful. You can measure very high pressures because let us suppose if you open the valve and if you try to keep more and more air, the pressure of this compressed air will increase and it can tackle a very high pressure defense also. Okay, so all these are the advantages of using inverted tube manometers. Acha, in your college you don't have manometer also, good. Fine, you can go to any labs in general. Okay, so like maybe if not in your college, then what you will do, go as a guest lecturer for any IIT or IISc, where not even IITs or IIScs, generally you can go for any of the some good local colleges where some of your friends are there, you can actually come. Okay, so please repeat once. Yeah, nothing much actually. We have calculated this pressure defense using this equation and this pressure defense using this hydrostatics, then we equated both, then we found out this y will be very much greater than x actually. That's it. Okay, so inverted tubes can be used for measuring even low pressure defenses and also for measuring the pressure defense very accurately. Okay, I'm in state government college, what more can be greater than this? Because of this what do you say, central government colleges then. Okay, so you dropped in IIT, yeah, unfortunately it happened because of HPCL. Like HPCL is not the reason, it's my choice. I plan to go to HPCL. Okay, and from HPCL I went to BRC, Baba Atomic Research Center, and from there I came here. Okay, fine. Okay, so x greater होगा ना सर? नहीं, देखिए. See, I'll just tell you, y by x is equal to rho f. No, y by x is equal to rho m minus rho f divided by rho f minus rho mi actually. Okay, if you see this value is greater than 1 because this is 12,600, this is only 900. Okay, or this is 1000, so this value is greater than 1, so y is greater than x. Okay, Clear? Got it? Fine. So then we'll look at next part, which is actually the hydrostatic forces. Okay. Till now the job is to calculate the pressure actually. Okay. Fine. So till now the job is to calculate what is the pressure acting at a particular point. Now the main next job is to know how much force this fluid will exert on any surface if you keep in fluid actually. Okay. So practically you can see we split this topic into two parts, plane and curved surfaces. Okay, maybe I think some 20 minutes, 15 minutes is left. We will, okay, fine. Before going for this, we'll solve certain numericals which could be helpful. Okay, like for example, I'll make you solve one manometer question which you feel easy sometime to solve this. Come on, let us solve this. I thought of solving all numericals one at a time, like this manometers means basically hydrostatics all together, like hydrostatic forces, pressure and its measurement, and motivation. Not motivation, sorry, balance and flotation. Okay, because someone is typing that. Fine. So see here, that water in a tank is pressurized by air. So you can see there is water in the tank and it's getting pressurized by air as shown in the figure. If H1 is 0.4, so this is H1, this is H2, and this is H3 obviously. 0.8 meters, and assume density of oil is 850, density of mercury is 39,600, then the gauge pressure of air at this location. Okay, so gauge pressure of air at this particular location is dash kilopascals, round off to 1 decimal place. Okay, now come on, round off to 2 decimal places. How we can do? This is a manometer, and let us start from this point 1 and let us reach all over this to point 2. Okay, we'll see how this actually happens. Okay, so let us start our discussion here and let us go up to this particular point. See, P1, you know one thing, as you go in the downward direction pressure increases, as you go in the upward direction pressure decreases obviously. So P1 plus, let us suppose from here to here if I move, the pressure difference between these 2 points is nothing but density of this water into G into this H1 plus H2 is the total gap, yes or no? Till this point, till this particular point, yes or no? Till this particular point, you can see the pressure difference between 1 and this point is nothing but rho of water into G into this total elevation difference between these 2 points, which is equal to H1 plus H2. Okay, so rho water G H1 plus H2 obviously. Okay, then after you can understand one more thing. Even though if I consider this pressure, again when I am going up, the pressure increase due to this column will be same as pressure decrease in moving up again, yes or no? So that's why we actually can delete this. Okay, so the pressure increase when you come in the downward direction is same as the pressure decrease again in this term. So that's why, like for example, if you take this x, you have to add plus rho water gx minus rho water gx, they get cancelled anyhow. Okay, so this fluid column will again cancel this fluid column. Okay, now whenever again you are moving up, this pressure difference between these 2 points is negative, so minus density of water into G into H2 is what you have. Okay, then after going from this point to this point, the pressure again decreases and it decreases by an amount. Density of oil G H1 is what you have. Okay, now from this point to again this point, the pressure at these 2 locations will be same because it is in static condition. So again coming down, H1 plus H2 is of oil, so plus density of oil into H1 plus H2 actually. Then you have reached this point. Then pressure at this point and at this point is again same. So obviously if you go up from here, this point and this point has a pressure difference of minus rho of mercury G into H3. Now you have reached this point and this point is actually open to atmosphere. So obviously the pressure at that point is PATM local. Did you all understand how I have formulated this equation? Clear? We have started here and we have traveled all over the length and finally reached this point 2 where the P1 plus, when you keep traveling across different fluid columns, multi-fluid manometer, someone has asked, you see 3 fluids are there in this. Okay, so this is how we have framed the equation. Is this clear to all of you till this point? Okay, is this clear to all of you till this particular point here? Yes or no? Like we were traveling across the fluid columns, that's it, and finally we are reaching a point. Now you can see, if you simplify this, undoubtedly this rho WGH2 term and this term gets cancelled. Rho oil GH1 term and this H1 term gets cancelled. So P1 plus rho water GH1 plus rho oil GH2, G is also there here, GH2 minus dou this mercury GH3 is equal to P ATM local. Okay. Now obviously if you want the gauge pressure, okay, so this is gauge pressure. So if you want to calculate the sorry, in all you forgot, oh, G, you know, every term there is G, no, obviously only in this term I have forgotten. Okay, so see here, if this is the case, then P1 minus P ATM local is actually equal to, so density of Hg into H3, G times of density of Hg into H3 minus density of water, because these two terms if they go to the other side we have negatives, so rho WH1 minus rho oil H2 actually here. Okay, so this is what we have, and clearly this P1 minus P ATM is nothing but P1 gauge. So the gauge pressure of air in the tank at this location 1 is what we will get if you simplify this value. Okay, so let us simplify. G, did they give you something 10 or something? Okay, so 9.81, fine, 9.81 into density of mercury, so 13,600 by default, yes, 13,600 into H3. So what about H3 actually? H3 is 0.8 minus density of water, what they have given you, so nothing is given, so take 1000 by default, 1000 into H1. So what about H1? 0.4 meters minus density of oil 850 is what they have given you, and H2 value is how much? 0.6. Okay, so this is 0.6 obviously. Okay, so if you simplify this, this answer will be in pascals. So if you want, what are the units they are asking in? They are asking in kilopascals. Okay, so you can convert this to kilopascals obviously. Okay, so let us first do the calculation. Let us take a calculator. 13,600 into 0.8. Okay, so this minus 13,600 into 0.8 minus 1000 into 0.4, 400 minus 850 into 0.6, 850 into 0.6 actually. Okay, oh sorry, something mistyped. So 13,600 into 0.8 minus 400 minus, okay, minus 850 into 0.6, 850 into 0.6. Okay, so this is the value multiplied with 9.81, 97805.7, 97805.7 pascals. So 97.8 80 kilopascals actually. Okay, so that's what we have. Yeah, 97.80 kilopascals is what we have, the pressure, the gauge pressure of air at this particular point 1. Okay, yeah, 97.805 roughly. Okay, so 1 decimal place, so 97.8 you can keep by default. Okay, so 97.8 kilopascals is the gauge pressure at this location when compared to atmosphere. Okay, simple question, no? Actually you start here, then travel through all the fluid columns and reach that particular point. Okay, so is that clear to all of you? Understood? Shall we slightly complicate the question more? Look, I think we have some other nice questions. Okay, so again, let us, will you solve this question? Like I'll give you this for homework better because you have understood. Now I have increased one more tube. Till now you have seen only one YouTube like this. Now I have put one more. Okay, so you can go, and it's an easy question actually, you can do. And yeah, because the time is also a bit short actually. Fine, we'll do one thing, we'll see some more questions maybe in tomorrow's class. We have some nice questions where I thought of teaching buoyancy also today, so buoyancy and manometric combined questions and all we have. Fine, okay, so anyway we will right now we'll stop at this point. So FM important topic chapter bata dijiye please. Dharmendra, to be honest I don't know astrology, so I cannot tell. Okay, पर लेकिन आपने पुराना साल का वेटेज लिया तो सब चैप्टर्स में वेटेज इक्वली डिवाइडेड ही है. Okay, it's like you have questions from every chapter, but I can tell you some least important, which is turbulent flow. That's it. Okay, पक्का, क्योंकि अगर वेटेज आपने देखा तो ऑन ए सीरियस नोट, इफ यू टेक ए वेटेज, वेटेज लाइक ऑलमोस्ट सेम फॉर ऑलमोस्ट ऑल द थिंग्स. ओके, हमको सिर्फ साइंस पता है बस. ओके, एंड यू ऑल्सो मेक ए हैबिट ऑफ, because you have already made your career as engineering. It's, let us suppose if you are a cricketer or something, you might have done something different, but since you all believed that education could make difference in your life, then definitely please focus on science and believe science. Okay, that will definitely create some good impact. So properties से तो कम आए questions नहीं, properties से बहुत ज़्यादा questions भी है. Inclined plate, you put a block, it slides at some velocity, bulk modulus, compressibility, many questions are there. Okay, हमारे पीवाई की बुक है ना आपके पास, so अगर आपने देखा तो बहुत सारे क्वेश्चंस है प्रॉपर्टीज में, पेर्जेंट्स मेजरमेंट्स में. ओके, लेकिन प्रोसेस ऐसे होना चाहिए कि इट्स नॉट लाइक ये चैप्टर इंपॉर्टेंट है वो चैप्टर इंपॉर्टेंट, ये नहीं है. ओके, प्रिपरेशन इज लाइक यू हैव टू प्रिपेयर फॉर द सब्जेक्ट. ओके, इट्स नॉट लाइक you have to let us suppose you are preparing only for gate. Okay, gate की पैटर्न पे क्वेश्चंस कर रहे, गेट की पैटर्न पे you are studying even the subject. मान लो कि अगर कुछ गलती से कुछ रीजन से आपकी गेट एग्जाम ठीक नहीं हुआ, सो तब क्या करते हैं, फिर आगे साल तक वेट करेगा क्या? नहीं ना, बीच में बहुत सारे PSUs आता है. ओके, सो बिना गेट वाला PSUs, बिना गेट इक्विपमेंट होता है. ओके, सो इस सारे एग्जाम्स में आप मैक्सिमम मार्क्स करना पड़ेगा. So how many marks we can expect from FM, sir? Again, if you check the weightage, around it can be like 8 to 9 or 7 to 8 marks, I can say. Plus 2 marks for hydraulic machines. So around some roughly 8 to 9 marks you can expect. Okay, from turbo and this. Last year it was very high, 12 marks, but generally the pattern if you see 9 marks tak aayega. Yeah. Okay, when is it going to come on end? This lectures will end on November 18th. Okay, fine. Okay, so we will stop here at this point for today, because again the time is very close. So we have talked about different pressure and its measurement techniques using manometers and bit of stuff. Guys, actually in the schedule if you see 10th to 15th it's holiday, because it's a holiday to all of us at PW. So November 10th to November 15th is holiday. Your Diwali is on 12th obviously. So if required, I will be taking only one extra class on the last day of the holiday if needed. Okay, clear? Because because of explaining certain things we are slightly in lag. So only one lecture we will be needing at maximum to compensate the things. So if required, I will take only one lecture as access in that holidays time. Okay, definitely, yeah. And but I'll make sure that you are getting definitely more than 90% of the marks in fluid mechanics if you attend all this thoroughly. Why I'm telling 90% is generally I guarantee 100% because it happens every year, but let us suppose this year if some question comes out of the box of all the people, then still my promise should hold good. That's why I'm taking. Okay, so fine. Anyway, so take more than one. Yeah, thank you. I'll see depending on the things how things progress in this kinematics and all, because when I start kinematics and all, you should have certain idea on vectors, because the velocity and all this stuff. But definitely don't worry, before I start any chapter, for the first 10 minutes I'll teach you the maths involved in that. Okay, like for example, let us suppose if I'm teaching kinematics, I'll explain you vectors, differentiation of vectors, curl, all these things. Okay, so don't worry. And for any thing that you feel that I can help you out, you can actually approach me at this group. Okay, so this is the Telegram ID, so you can definitely you can join that. That's majority managed by all our PW students, and even I'll post my views on your doubts and all if you have. Okay, साजी प्लीज XC का PYQs अवेलेबल करा दीजिए. हाँ ठीक है, प्लान में ही है, सो वेरी सुन आपको मिलेगा. but your concepts are depth which we need. Obviously गेट के लिए इतना concept पढ़ना ज़रूरी है. Okay, ठीक है, तब इस session end करेंगे हम. Fine. So I hope you all liked and enjoyed this session again. So in tomorrow's session we'll start with hydrostatic forces and buoyancy both. Okay, and we'll try to close up this statics in tomorrow's part. Okay, and in the next Thursday's class, no, today is Wednesday, right? So in the 5 days class we will look at kinematics. Okay, fine then. Exo motor world, my revision is not proper, I'm scared. We'll discuss, okay, how to revise and all when we find some time. Normally in flow through pipes, all these things we'll find some time. We will thank you sir, no waiting in YouTube. Alright, ठीक है यार, waiting के बाद fine, it's okay, you all, as long as you all understand, it's fine. I'm happy with that. Okay, so thank you all. We'll meet again on tomorrow at 7:30 AM. Okay, yeah, thank you.